So last time I will discuss the analytical property of free energy density, and we know that this f function, the free energy density, should be a convex up function in terms of all these parameters. And today we will introduce another important symmetry properties of the Ising magnet, and before we go into the detailed calculation, demonstrate this existence of a phase transition. So we could write down this Ising Hamiltonian like this, as we defined earlier, and we try to prove and demonstrate that there's a symmetry of this free energy density in the field and also in coupling constant J. First, write down the important mathematical identity involving any function of the spin, the local spin on any site I, which is to be summed over by taking the SI to be plus or minus 1 in the summation of this phi function as function of the spin, and this summation could be equally well expressed in terms of this phi as function of minus SI, because when we sum over both plus and minus 1 of the spin on every site, we could say that minus SI is also taking the value of the plus or minus plus 1 in the summation. So it doesn't matter whether we write it this way or that way, so they're all equivalent. So we will use that property later. Okay, but there's a very important symmetry of the Hamiltonian of the Ising model at any finite size, which is called time reversal symmetry. Namely, we should perform the time reversal transformation of the Hamiltonian by flipping both the sign of the spin and also the sign of the field. Okay, if you are familiar with the quantum mechanics, and you know that when we perform the time reversal of the Hamiltonian, we change the time from t to minus t. But in order to show that this Hamiltonian is invariant under such a transformation, this Hamiltonian should be invariant under simultaneously flipping the sign of the field, because the field is sort of proportional to time versus the electric field. So there's a time dependence implicitly in this magnetic field. And also the spin is angular momentum. Angular momentum is actually a function of time as well. So when we perform the time reversal transformation, we should flip both the sign of this field and the spin. And if I flip these two couplings, the signs, then if the Hamiltonian is still invariant, then I can say that this Hamiltonian is invariant under time reversal transformation, or this Hamiltonian is having the time reversal symmetry. So we can use that. You can see clearly what it means when you apply this time reversal operation for the Ising Hamiltonian. If I flip this H and S at the same time, minus subscript plus, so it goes back to this positive sign. And if I flip this SI to minus SI, also Sj to minus Sj, again minus subscript plus, so it leaves the Hamiltonian invariant. So indeed, the Hamiltonian has a time reversal symmetry under such a transformation. So we can further show that the partition function for this Ising magnet or ferromagnet is actually even function of H. So it is the same if we calculate the partition function as a function of H, J, and T as that partition function if I flip this field from plus H to minus H and I calculate the partition function, I get the same value. So there's a symmetry for the field when we calculate the partition function. So in other words, we will show in just a moment that the free energy coming from this partition function is also having such a symmetry in H, namely it is an even function in the field. So let's try to derive such a relation. So first we will show that the partition function has that symmetry when we flip the sign of this field, and to do so we could just write down the partition function for the flipped field, and we could just spell it out. The definition of the partition function the sum over this Boltzmann weight, and the summation is over all these different spin configurations plus or minus 1 for all the sides of the spin. Okay, so but we can rewrite this summation in terms of the similar summation, but we change the sign of the spin by using this identity there. So since this partition function is a function of the spin and with the summation over there, and so it should be equivalent to write down the partition function in terms of minus Si. So I can freely change the spin, the side I, to minus the spin. So then we could simply just redefine everything. So I can just show that this is the same as if I change my spin notation. If I define my spin on side I, a new variable called S bar I, which is what, minus Si. But this is, the new variable is always the same as before when you sum over all possible values of Si or S bar I. But then we could simply just absorb that minus sign in that Zeeman term. So, and I define this minus Si as S bar I. Okay, so this summation is equally well expressed in terms of this S bar I minus beta omega Hj S bar I. But this summation over Si or S bar I are dummy indices to be summed over. So I can relabel a spin on every side. Say, I can just recall this S bar the Si. I can simply just call this variable whatever I want. Okay, so I remove the bar. It doesn't matter after the summation over all possible spin orientation. So this is the same thing. So then I put this back, this Si, in my summation by simply just redefine my S bar as S. So then we complete the circle. So in this form, the partition function, the sign in front of the H, the field, is actually plus, but then in the beginning, this is minus. So this is the same as what? Z omega H J and T. So in other words, I can use this time reversal symmetry of this Hamiltonian by simultaneously flip the sign of the spin and the field, and we can show that the partition function in this negative field direction is actually having the same value of the field along the positive direction. And if you take a log of this partition function, you will get precisely this conclusion that the free energy coming from the Ising ferromagnet is actually an even function in H. So, but there is more to say about the symmetry of the Ising model. Namely, we can show further that the statistical properties of an Ising ferromagnet is actually the same as that for antiferromagnet. Even more, that at zero field and on a bipartite lattice, and all these properties of an Ising ferromagnet is having the same properties of Ising antiferromagnet. So this is a more stronger statement which we didn't realize at the beginning when we introduced the Ising model. And this is really highly non-trivial statement, so we will just prove this right now. So at zero field H equals 0, we don't have that Zeeman term, H times sum over I Si. We don't have that term. The only term we have is the spin-spin coupling. So for a ferro Ising model, this is given by minus J sum over nearest neighbor site of SIA times Sj of B, where A and B are referred to the lattice points or lattice size on the bipartite lattice. So let me just define one more time what I mean by bipartite lattice. It means that in that lattice, we are able to define two separate sites or two groups of sublattice structures, which I call this sublattice A and sublattice B. And by calling them sublattice, I mean both A sublattice and B sublattice are just a square lattice, for example, in 2D. Okay, so let me just finish this. And B and B. You could consider this square lattice as an interlocked combination of two sublattices A and B in such a way that sublattice B is actually inserted into sublattice A. So it's kind of interlocked two sublattices of A and B to form a square lattice. So if any lattice have such a properties, then we call this bipartite lattice, because we could partition the lattice in terms of a two, which is the meaning of a bi, two different groups of sublattices, A and B. And indeed, the square lattice belongs to such a case, so we call this square lattice a bipartite lattice. Of course, the square lattice is not the only possibilities or examples of this bipartite lattice. There are other examples of bipartite lattice which we'll discuss later. But we could rewrite this Ising coupling in terms of the interaction of the spins on different sublattices. Say, if the side I is on A sublattice and the nearest neighbor side J should belong to the sublattice B. So if the Hamiltonian of the Ising model for a ferromagnet could be expressed in terms of that kind of form on the bipartite lattice, then there's a symmetry of the system. Namely, we could go from the positive J to negative J system by either flip the sign of the spin on sublattice A to minus SIA, or by flipping the sign of the spin on sublattice B, but not both. Okay, which means that this Ising model for a ferromagnet on this bipartite lattice is equivalent to the Ising antiferromagnetic system. So for example, if J is positive, then this is a ferro, and minus J is actually describing the antiferromagnetic couplings between the two spins, and they are equivalent because we could either flip the spin on sublattice A or a spin on sublattice B, but we cannot flip the spins on both sublattices. But we can do that because, as I mentioned, when we calculate the partition function, we need to sum over all possible spin configurations, and we can easily flip the definition of the spin on sublattice A to minus SI, and at the same time, we could flip the sign of the J so that the partition function are, in both cases, are identical. So let's take a short break. When we come back, we will finish this proof and derivation of equivalence between the Ising ferromagnet and Ising antiferromagnet on a bipartite lattice to derive the conclusion that the Ising ferromagnet is actually equivalent to the Ising antiferromagnet in the absence of the field. As I defined earlier, that on this bipartite lattice, the Hamiltonian of a Ising ferromagnet is given by this minus h sum over I and j nearest neighbor sites, SIA times SJB. Okay, so there's always the interactions are between the sublattice A and sublattice B of that spins. So there's no interactions of the spins between the same sublattice sites. There's always the interactions between different sublattice sites A and B. So in other words, if I write down Hamiltonian in the absence of field, the ferromagnetic Ising model with a minus j in front, and SA and SB are the non-flipped spins, then it is equivalent to rewrite this Hamiltonian in terms of the plus j, but then the sublattice A spin is actually flipped into minus SA. But the spin on sublattice B is still SB. We don't flip spin on both sublattice sides. Remember, there's either spin flip on sublattice A or on sublattice B, but not both. So you can very easily see this equivalence because you could simply just absorb this minus sign either in the redefinition of spin on sublattice A or the spin on side J while keeping the Hamiltonian invariant. So that's really trivial observation that you could just absorb this minus sign in terms of a new definition of SIA to be the minus SIA, or SJB change to minus SJB. But you cannot simultaneously flip both spins on I and J because obviously you get only one minus sign but not two minus signs, so that's all. Okay, but the consequence of this identity is that the partition function for a ferro Ising model is actually equivalent to the partition function for antiferro, where this J is actually carrying a plus 1 prefactor. So let me just remind you what it means for Ising ferromagnet and Ising antiferromagnet. So the Hamiltonian for ferro and antiferro, they differ by a minus sign as a prefactor in front of the J. So, but the ground state are different because in the ferro case, to minimize this free energy coming from the Hamiltonian for a ferro Ising model, the spins must be parallel to each other because this is the only way that you could minimize the total free energy, which is a negative value. Therefore, you should maximize that negative value. And the only way to maximize the negative value is by either all the spins pointing up, that kind of a configuration, or all pointing down. So all the spins are pointing up or down are the solutions or the ground state of the Ising ferromagnet in the absence of field. But if you change the sign of a J, minus J to plus J, then the ground state configurations are different. Namely, in order to minimize the free energy or maximize the negative value of free energy, since it's the plus J and J is positive, so you should either having upspin on side I, but downspin on side J, or vice versa, because plus 1 times minus 1 is actually minus 1. Okay, it's the same as minus 1 times plus 1. So it's kind of a trivial statement, but then you could see the difference between these two, Ising ferro and antiferro, in the sense that for Ising ferro, all the spins are perfectly aligned in the same direction, but in the antiferro case, the spins are alternating patterns along the bipartite lattice. But from statistical mechanics point of view, the Hamiltonian has such a symmetry, and we could redefine my spin on side I or side J to be negative of that original convention. Say, for example, if I could simply just redefine all the spins on, say, sublattice B to be minus SB for the original orientation, so all the spin up in the antiferro becomes spin down in my new convention. So the up-down orientation for the antiferro Ising model will become Ising ferro because now my new spin on sublattice B is actually changed to, say, spin down in my new convention. So up, down is changed to all up or all down. And likewise, I can simply just recall all the sublattice B for Ising ferro minus the original spin on that sublattice, so that I can artificially flip the spin just because my definition is changed. I redefine spin direction to be along the negative axis, negative z-axis relative to the previous arrangement. But the physics is the same, so that Ising ferro in the new basis becomes Ising antiferro, and Ising antiferro becomes Ising ferro if I simply just redefine my spin on either one of the sublattices to be negative of that original sign. Then I can easily flip between the Ising ferro to Ising antiferro, right? So that's the magic. So in a way, that thermodynamic point of view, the partition function for Ising model on the, say, square lattice or bipartite lattice are exactly the same as the Ising antiferro. All right, so we will come back to that later part of this lecture to address this equivalence between the Ising ferro and Ising antiferro. But this kind of a beautiful equivalence does not hold for any arbitrary lattice because we need bipartite lattice in order to make that statement or see this equivalence. But on, say, on triangular lattice or other complicated lattice, we don't have such a identity. So in that case, the ferromagnetic Ising model would not be equivalent to the antiferro Ising. So let's come to the real analysis of Ising ferro at t equals 0 and see how the phase transition occur. Okay, so at t equals 0, or beta is actually 1 over kBt goes to infinity. So we discussed the phase diagram of that model. Again, so let me include the field, which is the Zeeman term, say minus h psi, and the partition function is this, and we are interested in knowing the ground state configurations. That means when temperature goes to 0. So, but we don't need go to the thermodynamic limit, which means that the volume goes to infinity to see the phase transition. The phase transition for this Ising ferromagnet at 0 temperature in 1D is exactly happening at 0 temperature. 1D Ising ferromagnet as a phase transition exactly at t equals 0 and 0 field limit, h equals 0. So we will see that in just a moment. This is just the simplest possible case to identify a phase transition in any statistical models. So let's just evaluate this magnetization at any finite size, which is the average moment when you sum over all the spin moment on all the sides. But we know very well that this is actually +1 if h or the field is actually positive, and -1 if h is negative. And this is because the spin moment on all the sides, or every side, is actually +1 if h is positive, and -1 when h is negative. Okay, so as I mentioned, at 0 temperature, all the spins would like to point in the same direction. They arrange perfectly in an array such that all the spin orientations are the same. But whether the spins are pointing up or down depending on the sign of the field. Remember, there is a Zeeman field here coupled to the local spin. So suppose the h is positive, then again, to minimize the free energy, including the Zeeman energy, all the spins should be +1, right? Okay, so likewise, for a negative h, or along the negative direction relative to this plus h, then this is actually minus mass plus times the magnitude of the magnetic field times the spin, sum of the spin. So in this case, this SI should flip the sign because we need to maximize the negative value of the free energy or minimize the free energy. So that's the trivial results that's just coming from the Zeeman energy, to minimize the Zeeman energy when we apply this just a tiny little bit field. So you can see that the phase transition occurred along the field direction, that at 0 field, you don't have magnetization, or there's a jump right here, but in the positive h direction, you have all the spin pointing up, but for the negative h side, you got all the spins pointing down. Okay, so there's a phase transition between this all spin up state and all spin down state. So this is precisely this 0 temperature phase transition for Ising ferromagnet when this field is actually very, very tiny applied to this system. Okay, so you can see that the spin orientation suddenly changes sides near this 0 plus or 0 minus of the applied magnetic field. So you could very easily see that from this kind of trivial solutions, you can calculate the magnetization for this positive field direction or negative field direction, and that is the phase diagram. That's really trivial. But what is slightly non-trivial is that what about the finite temperature? Is there any finite temperature phase transition for one-dimensional Ising ferromagnet or two-dimensional Ising ferromagnet? For a one-dimensional Ising ferro Tc, which is the transition temperature below which we have a long-range magnetic order, and above which we don't have a long-range magnetic order, and the Tc for a one-dimensional Ising ferro is actually 0, which means that at any given finite temperature for a one-dimensional Ising ferromagnet, the spins will be no long-range order, meaning the spins are disordered and the spin orders will be destroyed by the thermal fluctuations, which we call the creation of a domain wall. Okay, so any given finite temperature, a domain wall will be generated, and that domain wall is going to kill any spin order. But this is a one-dimensional Ising model. Two-dimensional Ising model, say for ferromagnetic coupling, Tc is actually finite, which means that below transition temperature, we have ordered the spins, but above Tc, you don't have ordered spin. But what exactly happening there in these two cases will become more clear next time. Okay, so our time is up for today, and we will continue discussing the fate of this state for our Ising model in both 1D and 2D cases next time. Okay, so see you next time.